I would like to talk about the Sunrise balloon mission. It's a balloon solar telescope. And first, I want to acknowledge that this is a very large international consortium. Max Planck Institute in Germany is the PI institution for the science. And here at APL, we are leading the gondola development. But we have also inputs from Japan and Spain for the science instruments. So what are the science questions for Sunrise? The key goal for Sunrise is to investigate the dynamics and the 3D structure of the solar magnetic fields throughout the solar atmosphere. We want to contribute on determining how the flux emerges and how it gets dissipated, and what is the difference in the quiet sun between where there is a corona hole and then not. And also we want to see how efficient is the field braiding that's important for corona heating. Sunrise has flown 2 times before, but it was limited to observe in the photosphere. And for Sunrise 3, we have modified the instruments. We added a capability so that we can observe at multiple altitudes, both in the photosphere and the chromosphere. And the chromosphere has a more dynamic, the magnetic fields are more dynamic, and it's key to understand how then the magnetic fields evolve into the corona. So why do we want to fly a balloon solar telescope? The main reason is that because we are above 99% of the Earth atmosphere, and that allows us to access the near UV that is not accessible from the ground. And we have sunlight for 24 hours a day, whereas for ground observatories, you are limited for daytime. So we can do a very long time series without having issue with the daytime cycles. And since we are above most of the Earth atmosphere, then we are not affected by the seeing. And so the light arriving from the sun is very stable. We can have a better understanding of what the actual point function is for the telescope. And we also are not affected by image blurring due to seeing. And the sky brightness is much lower. And of course, flying on a balloon is much cheaper than flying in space. So it's a better way to access a near space environment and have a high resolution imaging, because this is one of the other goals. We want to look at the sun on very high spatial resolution. And for comparison, I'm showing here on top the DKIST, one of the first light images from the DKIST 4-meter telescope, and that was obtained in the G band, I believe, and using phase diversity. And whereas in the lower right, the black and white image is from a UV image that was taken, near UV image that was taken with sunrise, with only some phase diversity processing, and you can see they are comparable in image quality. So is there an overview of the observatory? It's a very large gondola, carries a 1-meter telescope, and the suite of instruments is nestled on top of the telescope itself. And on the lower deck, we have an avionics box that carries all the electronics, all the control electronics, and also there's some electronics on the sides. The large solar panels facing the sun so that we can provide power for the entire observatory. And then on top, we have a suite of antennas for the telecommunication to the ground. And a lot of these details here on the left side, I'm going to provide them further on in my presentation. So let's start with the telescope. It's a 1-meter telescope developed by MPS, so originally built by a German company, Kaiser Traded. Was the third flight that he had. He flew on Sunrise 1 and 2. It's a Gregory Coudet solar telescope. So Gregory means that there is the focus of the primary mirror is in front of the secondary mirror, and at that location you can put a heat rejection mirror, and with just a little pinhole at the center of the mirror that allows you to pretty much reject 85% or more of the light coming from the sun, so reducing the heat load on the secondary. And the field of view of the telescope is about 3.4 arc minutes. The suite of instruments, we have three main instruments. They are all polarimeters. There is a UV spectropolarimeter that takes the full Stokes spectrum, so full polarization spectrum. And we heard from Excalibur what the Stokes spectrum is, the Stokes parameters are. And from 314 to 410 nanometers. And it can provide unprecedented spatial resolution and also height, because there are several spectral lines in that region that are both chromospheric and photospheric. Then we have an imaging spectropolarimeter, 2MAG. It's a Fabry-Pro-based imaging spectrograph. It provides 2D images of the sun at a specific spectral line, and then you scan across the spectrum, and we can scan across two spectral lines, one in the photosphere and one in the chromosphere. And then to cover the other part of the spectrum, we have an infrared spectropolarimeter that operates from 760 to 850 nanometers. And also there, the spectrum there, you can see you have several spectral lines that are both chromospheric and photospheric. And then there is another instrument that is the correlation wavefront sensor that allows you to stabilize the image at all the instruments down to about 5 milliarc seconds. So the gondola can bring you down to about 1 arc second, 2 arc seconds, and then this image, basically it's an image compensation system. It brings you down to the stability needed to achieve this very high spatial resolution. So the gondola point control system was one of the key systems needed to achieve the science goals. It was developed here at APL through a series of iteration of many different previous gondolas, starting from flare genesis in the late 90s, early 2000s. It is basically an alt-azimuth system. We have an elevation motor and that controls the elevation of the telescope, and then we have an azimuth flywheel system that orients the entire gondola in azimuth, so you can point in azimuth and elevation. And then we have a roll stabilization system with a horizontal flywheel that allows to stabilize the side-to-side oscillation, the high-frequency side-to-side oscillation, that allows to maintain very stable pointing. In order to for the attitude determination, we start with an IMU, a commercial IMU that gives you a rough orientation of the gondola in azimuth and elevation. And then at some point, the sun enters the optics of an intermediate sun sensor that can stabilize the image and can center the telescope and the sun to within a couple of arc minutes. And then at that point, we have a fine telescope that creates a 1-inch image of the sun on a quad cell, and that provides the information for the fine pointing information. And then the point and control computer uses PID controllers to control the 3 motors for the attitude control. So we flew, we finally launched on July 24. We had a previous launch attempt in July 2022, but an initial launch prevented us from doing science observation. And all the funding institution and also NASA were very gracious to be able to provide us some additional funding so that we can have a second chance. So we went back 2 years later. And after about a month of being flight ready, we were able finally to launch 1 day after Excalibur from Esrange in Sweden. The launch went very well this time. And the flight lasted about 6.5 days. An average float altitude of 120,000 feet. And the flight was very successful. We collected about 2 terabytes of data, and it was successfully recovered about a month after landing. And the data vault with all the science data was brought back to Germany, and we were able to extract all the science data. Quick word of our flight performance for the pointing. It was pretty much what we were expecting. On the left, you can see 2 plots. One, when the telescope is pointing at a relatively high elevation, and the lower one, when the telescope is pointing at a lower elevation. And you can see there is more noise in the error at higher elevation because it's more difficult to do proper azimuth pointing at the higher elevations. And the roll stabilization helps somewhat, but they're still more challenging to point at that elevation. One thing I have to say is that we had to actually relax the gain in our pointing control loops because at first they were too tight, and the image compensation system was not able to operate because there was too much introduction of noise. So we had to actually relax them, and then the image motion compensation was better performing when we had a more relaxed gondola pointing. But in any case, throughout the entire flight, the pointing errors were within the lock requirement for the image motion compensation, which was about 40 arc seconds. Just a few words about the performance of the other systems. In terms of power, we generated about 900 watts on average. And as you can see, if you look at the sun elevation plot, there is a day-night cycles in the power generation because when the sun is very low, we have heaters turning on that basically the gondola requires more power. And for the last 3 or 4 kind of almost night cycles, the sun was very low and was kind of lower than what we were originally designed, but that was because we launched kind of late in the season. Otherwise, all the system operated really well, and the temperatures of all the systems were within our operating range. In terms of observation, here's a sample of all the types of observation we've done throughout the 6 days. Those are thumbnails. We observed sunspots, emerging regions, quiet sun. We did observations at the sun limb. In the, I think is, in an emerging region, we also, we were observing while there was an M-class flare going on, so that we were able also to observe the dynamics for when the flare occurred. So it's really a treasure trove of data, and it will take a long time to go through all this data, and we will provide this data to the entire scientific community once we are completed with the data reduction. Here's some more details on some first reduced data. All these images, they span from the near UV on the left with the SUSY spectrograph. You can see a phase diversity reconstructed image, and you can see the level of details that we're able to achieve. In the middle section shows from filter graph images from 2MAG, both in the photosphere and in the chromosphere. And on the right side is slit jaw images from the near infrared spectrometer. And on the lower right, you can see magnetic fields that we have reconstructed magnetic fields both in the photosphere and in the chromosphere. Yeah, and this is my last chart. So concluding, the flight was very successful. We collected more than 200 terabytes of data, and the team right now is still working at reducing the science data. There's always little issues, little quirks that need to be worked on before we can do a full release. We expect to be able to release to the general community the data by the end of this year. If people want to have more information, I have here the website for the Max Planck Institute sunrise page. Also, the 2MAG instrument has a web page. And we have, this year, we have published a number of articles on solar physics. The first one that I'm listing here is an overall overview for the entire mission and the observatory. And the second one is the one that we published just recently, describing the gondola. And there are other articles describing the individual instruments. And this is all I have.